Good afternoon. We are going to do the problems on magnetic circuits problem. The first problem statement goes as follows. A coil of 200 turns is wound uniformly over a wooden ring having a mean circumference of 600 millimeter and a uniform cross-sectional area of 500 mm square. The current through the coil is 4 ampere. So 200 turns and 4 ampere. So which means 800 ampere turns is the MMF. Calculate H, B and total flux. That is what is being asked. So let's try to do this problem. So it says problem number 1. It is wooden ring. So very clearly you are not going to have any relative permeability. The relative permeability is going to be 1. So mu equal to mu naught multiplied by mu r, which is 4 pi multiplied by 10 power minus 7 multiplied by 1. So this is going to be 4 pi multiplied by 10 power minus 7. And I think we told this unit as Weber per ampere meter. That was, if you may recall, how we derived the unit for this permeability. We said MMF divided by flux will be equal to reluctance, which should be equal to ampere turns. So ampere divided by Weber. This is the unit for reluctance. And reluctance, if I say this is R, so reluctance R is L divided by mu A. So I should say mu is equal to L divided by A and the reluctance here. So L is meters and ampere is meter square. A is meter square because this is area. So I'm going to have 1 divided by meter and I'm going to have ampere per Weber. So this is going to be ampere and on the top it is going to be Weber. So I can say this is Weber per ampere per meter, or Weber per ampere is, we wrote this equation also, L di by dt equal to N d phi by dt, from which we wrote L is equal to d phi divided by di multiplied by the number of turns. So this is Weber per ampere. That is inductance unit, which is Henry. Inductance unit is Henry. So Weber per ampere is Henry. So I can write this as Henry per meter. So I should be able to say this, whatever I have written here, that is actually permeability, which has to be written in the form of Henry meter power minus 1. That is the unit as far as the permeability is concerned for wood or any other substance. Now what is being given is the number of turns is 200 and the length of the magnetic circuit is given as 600 mm. I think what is given is circumference is 600 mm and the cross-sectional area is 500 mm square. So I should write A is equal to 500 mm square. Okay, and current is given to be 4 ampere. So now what is being asked is, you are being asked to solve for what is magnetic field intensity H, and you are being asked to calculate what is the flux density and then the total flux. I think these are the 3 things that are being asked. So We can calculate the magnetic field intensity as mmf per the unit length of the magnetic circuit. So mmf is going to be 200 multiplied by 4 divided by the length of the magnetic circuit, which is 600 multiplied by 10 power minus 3 in terms of meter. Right? So this is going to be 8 divided by 6. Right? Multiplied by, or 8000 divided by 6. That is what it is. Right? So that comes out to be 1333.33. So that is, the unit will be ampere turn per meter, or turns do not have any dimension. So I can write ampere meter power minus 1. Okay. So this is going to be H. Now what is B? B will be H. B by mu is H. Right? So I can write H multiplied by mu is B. So I should be able to write this as 1333.33 multiplied by mu is 4 pi into 10 power minus 7. So this is going to give me in Tesla, or this will give me exactly what is Weber per meter square. Both are one and the same, Tesla and this. So this is coming out to be 1.6755 millitesla. This is what we are getting as the answer. Please verify it. Whatever I have done, please verify it. Total flux is going to be area multiplied by B, which is flux density. Okay. So I can write this as 1.6755 milliweber per meter square. That is also fine. Okay. Or into 10 power minus 3 Weber per meter square. That is also fine. So I can write this as multiplied by 10 power minus 3 Weber per meter square. Now this area happens to be 500 millimeter square, which will be 500 multiplied by 10 power minus 6 meter square multiplied by 1.6755 multiplied by 10 power minus 3 Webers. Okay. So this is coming out to be 0.8378 microweber. That is what we are getting as the answer. Please verify this, but this is what I'm getting as the answer. Any questions on this? Any questions? Any questions? Let's look at problem number 2. So problem number 2 says, calculate the MMF required to produce a flux of 0.015 Weber across an air gap of 2.5 millimeter long, whose effective cross-sectional area is 200 centimeter square. So length is 2.5 millimeter and area is 200 centimeter square. Okay, so let's try to first of all write this. So cross-sectional area is 200 centimeter square and length of the air gap length L is given as 2.5 mm. And the flux required is 0.015 Weber. This is what is given. Okay. So you can directly calculate B and do it that way. Or if you want to calculate L mu L by mu A, that is the reluctance. And you can say R multiplied by phi is MMF. That is also fine. Okay. So what is being asked is what is the MMF? How much is the MMF? That is what is being asked. So you can do it either this way, L by mu A equal to reluctance, reluctance multiplied by flux is MMF, that is also fine. Or you can calculate what is B, B is phi divided by A. Okay, so that is going to be 0.015 divided by 200 multiplied by 10 power minus 4. This is going to be our area of cross section in meters. Okay, and this comes out to be 0.75 Tesla. This is the flux density that we are getting. And you can write B divided by mu. In this particular case, it is mu naught equal to H because it is air gap. So mu is going to be equal to mu naught for air. So I can write H is equal to 0.75 divided by 4 pi into 10 power minus 7. Okay, so you should be able to get this, how much this is. This will be ampere per meter. Now this H multiplied by length of the magnetic circuit, which is 2.5 millimeter. So that is 2.5 multiplied by 10 power minus 3. This is going to be the MMF required. Any questions on this? So problem number 3 says a mild steel ring having a cross-sectional area of 500 mm square and a mean circumference of 400 millimeter has a number of coils to be 200 turn coil. It is wound uniformly around it. Calculate the reluctance of the ring and current required to produce a flux of 800 microweber in the ring. Mu R of mild steel is 1380. So I'm not going to do the calculation. We'll just look at the method and be done with that. Okay. So this is problem number 3. So what is given is number of turns is given and area of cross section is given. Then length of the magnetic circuit is given, flux is given, and mu R is given. All these things are given. Calculate the ampere, the current required to produce this flux. That is what is being asked. Okay. So we know that if I know the flux multiplied by reluctance will give me N multiplied by I. That is number of turns multiplied by the current. Now, how will we get the reluctance? How will we get the reluctance? Yes, anybody? How will you get the reluctance? It is L by mu A. So I can write this as L divided by mu naught mu R A. So whatever is the L given, which is 400 millimeter, and mu naught mu R I can write as 4 pi into 10 power minus 7 multiplied by 1380, which is mu R, multiplied by the area. Area is given as 500 millimeter square. So this will give me reluctance. And what is the unit of reluctance? It will be ampere per Weber. This is going to be the unit of reluctance. Okay. So once I get that, I should be able to multiply that reluctance, whatever I got, with that of the flux given, which will give me number of turns multiplied by current. I have been given number of turns, which is actually 200. This is given as 200 turns. So I can divide whatever I get as flux multiplied by reluctance. That has to be divided by 200 to get what is the current value. Okay, fine. Any questions? Any questions on this? So let us look at problem number 4. In the above problem, if a small radial air gap of 3 mm long is cut in the ring without changing the excitation current, how much will be the flux produced in the air gap? Neglect fringing effect. So I have originally the ring which is not having any gap at all. So I am just looking at this ring somewhat like this. This is the ring. Okay. Now what is being said is a small 3 mm gap is being created. So this is the air gap. This is 3 mm gap. Air gap is being created. Okay. And this is having uniformly wound wire. So let us say it is somewhat like this. I'm going to have the wire wound somewhat like this. So this is the wire that is wound around. Okay. So I'm going to have a current I flowing like this. And the current in the last problem is 1.845 ampere. That's what I am getting. Please verify. So in the previous thing, I am getting the current to be 1.845 ampere. Verify it, because if it is not all right, if I have made a calculation mistake, you should find out. So let us say this is 1.845 ampere. And the number of turns is 200. Now the reluctance of the air gap, reluctance of the magnetic circuit is going to be reluctance of the ring plus reluctance of the air gap. These two have to be added together. And that is what is the total reluctance. Okay. So if we say that the original length of the ring is 400 mm. Now I should say, so this is the original length. So I should say now 397 mm is length of ring, whereas 3 mm is air gap length. Okay. So I should be able to calculate, assuming no fringing. I'm going to assume that whatever is the air gap magnetic flux line, everything is going to pass straight ahead. So I'm not going to have the cross-sectional area any different along the air gap as compared to what I'm having along the iron ring. So I'm going to say that in this particular case, A is air gap area, cross-sectional area, as well as steel ring cross-sectional area, everything is going to be 500 mm square. Okay. So I should be able to write this as reluctance of the ring. I can write as 397 divided by 1380 multiplied by 4 pi into 10 power minus 7. So L by mu and A is 500 mm square. So 500 multiplied by 10 power minus 6. This is 397 multiplied by 10 power minus 3. So this is going to be the reluctance of the ring. Then reluctance of the air gap will be 3 multiplied by 10 power minus 3 divided by, now there is no 1380 because this is air gap. So I'm going to have 4 pi multiplied by 10 power minus 7. And this has to be multiplied by the same cross-sectional area. So this entire thing comes out to be the total reluctance. And what I am getting as per this is some 45.79 into 10 power 4 Henry per meter. And this is coming out to be 47.75 multiplied by 1, 2, 3, 4, 5. So multiplied by 10 power 5. Okay, so this is the kind of overall reluctance. Please note the difference. So this is definitely going to be having at least a 10-fold difference. Okay. So this is actually coming out to be totally some 5.2325 multiplied by 1, 2, 3, 4, 5, 6. So 10 power 6. 10 power 6 Henry per meter. This is the reluctance. Okay. So this is the reluctance. This is Henry per meter. No, this is actually ampere per Weber. Right? Because we are talking about reluctance, and reluctance is phi. This is essentially ampere turns per Weber. That is what is reluctance. So I'm going to have ampere per Weber as the unit. Now, this is the reluctance and MMF remains the same. So you should be able to calculate the flux. MMF is still the same current, original current what I have got. That is 1.845 multiplied by 200 ampere. Okay. Now MMF divided by this reluctance. So MMF divided by the reluctance is going to be flux. So this comes out to be 0.7052 microweber. Okay, so this comes out to be 0.7052 microweber. So if you look at this, in the last problem, when we looked at the previous problem, that flux that was given, let me look at this also. So the flux that was given in the third problem was 800 microweber. From 800 microweber, it has decreased to 0.7 some Weber. So which microweber, which means it has almost it has had quite a bit of reduction. Is that so? So this is coming out to be almost 100th, right? Or more than that. So it is having really a large amount of reduction in the flux. Please remember, whenever you cut an air gap, because it increases reluctance exorbitantly, you are going to have very minimal amount of flux coming up. So the flux, what you see in an air gap will be really, really small as compared to what you saw in a ferromagnetic material. So you are going to have really, really small amount of flux that is being created because of the introduction of even a small air gap. Okay, so that's what you are going to see normally when you introduce an air gap. Any questions on this? Any questions? So whenever you see that two of them are in series, the two reluctances, you are adding them together to get the overall reluctance. That's what we had done in the previous problem, because the air gap comes in series with the entire iron ring. So that is the reason why we are getting both of them added together as the total reluctance. Okay. So let us look at problem number 5. So problem number 5, the statement goes as follows. An iron ring has a mean diameter of 15 centimeter and a cross-sectional area of 20 centimeter square, and a radial air gap of 0.5 millimeter is cut in it. The ring is uniformly wound with 1500 turns of insulated wire, and a magnetizing current of 1 ampere produces a flux of 1 milliweber in the air gap. Neglecting the effect of magnetic leakage and fringing, calculate the reluctance of this magnetic circuit and mu r of iron. That is what is being asked. So MMF is 1500 multiplied by 1 ampere, which is 1500 ampere turns. Let me write that down first. So I'm being given MMF equal to 1500 ampere turns. Okay. The second thing that is given is it has a mean diameter of 15 centimeter and a cross-sectional area of 20 centimeters square, and air gap is 0.5 mm. Okay. So I'm going to say that L is 15 centimeter. And length of the air gap is 0.5 millimeter. Very, very small air gap. And area of cross section is given to be 20 centimeter square. Okay. And what is given is produces a flux of 1 milliweber in the air gap. So 0.001 Weber in the air gap. So I should say 1 milliweber, which is 0.001 Weber, is being produced in the air gap. So now two things are asked. One is reluctance. And the second thing that is being asked is what is the relative permeability of mild steel. These are the two things that are being asked. So the first thing to solve for reluctance, it's pretty simple. MMF divided by flux. That is going to give you what is the reluctance. So I can say 1500 divided by 10 power minus 3. 1 milliweber. That's what is given. So it is 10 power minus 3. So I can say it is 1.5 into 10 power 6 ampere per Weber. This is going to be the value of reluctance directly. Okay. So now you can calculate this reluctance, whatever we have got. This 1.5 multiplied by 10 power 6. That is going to be equal to L mild steel divided by mu naught mu R mild steel and area of mild steel plus, because it's radial air gap, both of them come in series. I should say L of G divided by mu naught multiplied by A of G. So I can calculate this as Lm is 15 multiplied by 10 power minus 2 divided by mu naught, which is 4 pi into 10 power minus 7. Mu R has to be here, and you have to calculate this area. Area is how much? Area is 20 centimeters square. So 20 multiplied by 10 power minus 4. So this is one portion. The other portion is going to be Lg, which is 0.5 multiplied by 10 power minus 3 divided by 4 pi into 10 power minus 7 multiplied by 20 multiplied by 10 power minus 4. So from which you should be able to calculate what is mu R. Only unknown is mu R. So please calculate mu R from this. Okay, fine. So this is going to be mu R, and I think I'm getting mu R value to be, please check it up. Mu R value is, I'm getting this to be 144.114. So this is the relative permeability I am getting. Okay, so please check it up. Please check up all the calculations, whether they are done properly or not. Because if I have done it in a hurry, it could have been wrong in some way or the other. So please make sure that you check it up properly. Okay, so let's look at the next problem. Problem number 6. A magnetic circuit made up of iron has a uniform cross-sectional area of 5 cm square and a length of 25 cm. A coil of 120 turns is wound uniformly over the magnetic circuit. When the current in the coil is 5 ampere, the total flux is 0.6 milliweber. At 1.5 ampere of current, the flux is 0.3 milliweber. For each value of current, or other these two values of current, calculate H and mu R of iron. So that is what is being asked. Okay, so let's try to do this problem. So problem number 6 basically tells that it is made up of iron. The magnetic circuit is made up of iron, and area of cross section is given as 5 cm square and length is given as 25 cm. Okay, and the number of turns is given as 120, and there are two values that are given, that is at I equal to 5 amperes, flux is 0.6 milliweber. And another value that is given is I equal to 1.5 ampere, which is less than 1/3. Please remember, it is only 1.5 ampere. Had it been 4.5, this would have been exactly 1/3. But the flux is not 1/3 or even less. It is 0.3 milliweber. Which tells that the flux is not linearly related to the current. So this is one conclusion, especially in iron or any other ferromagnetic material, flux will not be linearly related to the exciting current. This we would see time and again in any ferromagnetic material. We'll talk about this as we go along. So in general, in iron, you are not going to see flux and current are linearly. They will not be related linearly. Okay. So now in this particular case, these are the two values that are given. Now what is being asked is calculate H and mu r in the two cases. That is what is being asked. Okay. So if we neglect fringing and so on, so we can talk about, first of all, the flux is 0.6 Weber. So case 1, flux is 0.6 milliweber. So B is going to be, we are going to get 0.6 milliweber divided by the area of cross section, which is 5 multiplied by 10 power minus 4. So I'm going to get essentially 0.6 into 10 power minus 3 or 6 into 10 power minus 4. So I should get 6 by 5 multiplied by, that's it, 6 by 5 Weber per meter square. That is what we are going to get as the flux density in first case. We are talking about I equal to 5 ampere case. And 0.6 is the flux density. And we can calculate what is H. H is Ni by L. So Ni 120 multiplied by 5 ampere. That is mmf divided by L. L is 25 centimeter. 25 multiplied by 10 power minus 2. Right? So you are going to get this as, this is 600, right? 12 5s are 60. So we are going to get 600 divided by 25 into 10 power minus 2. Okay. So this is going to give us 600 by 25 is 24, I think. So we are going to get 2400 ampere meter power minus 1. This is what you are getting as the magnetic field intensity at this particular value of current and at this particular value of flux. Now, after all, B divided by H equal to mu naught multiplied by mu r, from which mu r can be inferred. Okay. So mu r, what we get here, actually I was getting 398. Verify it whether this is 398. Let us look at case 2. So in case 2, it is phi is 0.3 milliweber. So I can say B is equal to 0.3 into 10 power minus 3 divided by 5 multiplied by 10 power minus 4. Right? So I'm going to get 3 by 5. Basically, we are going to get 3 by 5 or 0.6 Tesla as the flux density. So if this is the flux density, again I should be able to write B divided by H, where H is going to be, how much is the current? The current is given to be 1.5 ampere in the second case. So 120 multiplied by 1.5. So I'm going to have H equal to 120 multiplied by 1.5 divided by the length of the magnetic circuit, which is 25 centimeter. So this is going to be the H value in ampere per meter. Now B by H I can use, which is equal to mu naught multiplied by mu R. Okay. So in which case we are getting mu R to be 663. Okay. So that is coming out to be mu R. Please note, when you are having lower current, that is 1.5 ampere of current, you are having mu R value to be 663. Whereas when you are having a higher current, which is 5 ampere of current, your mu R comes down to 398. So what happens in an iron is, generally if I try to plot what is the current and what is the flux that I am getting corresponding to current, you might see that it is initially going linearly and then it saturates. Normally you will see saturation only in ferromagnetic materials. So the saturation has to be taken into consideration whenever your exciting current happens to be pretty large. The more the current, the more saturation it will manifest. So you will not see a proportionate increase in the flux. So this is flux in Weber and this is going to be current in ampere. When you are trying to look at how these two are related, initially it may be linear, after that this saturates. So this is going to be saturation region, whereas this will be linear region. Okay. We will see why saturation occurs in ferromagnetic material eventually, but this is the way generally your characteristics are going to be, and that is what is manifested here. Because the current may be increasing, but the flux does not increase correspondingly. So you are going to have initially, when the flux and current are proportionately increasing, this will be higher, mu R will be higher, but eventually it will become lower. Okay. So this happens in saturation region. Just wanted to mention this so that you guys will be familiar with saturation eventually when we talk about it. See, seventh problem. Seventh problem is a magnetic circuit made up of iron, mu R is 400, is arranged as shown. Figure A is shown here. So figure A shows that you are going to have a small air gap here. Please note there is a 1 mm air gap here. And you are going to have this as 340 mm length, this complete magnetic part. This is another 340 mm length. And this is 150 mm length. Okay. And cross-sectional areas are given. Cross-sectional area, the side ones are going to have 500 mm square. And the center one is having 800 mm square. So let us try to draw the equivalent magnetic circuit for this. So what you would see is that here is the MMF, which is from the central limb. And I'm going to have one as reluctance of iron. And another one as reluctance of air gap, along with the wound coil. So if you look at the overall figure, you do have a wound coil here. The wound coil is actually having the reluctance of the limb and also the reluctance of the air gap. But in these two sides, it is going to be reluctance of iron only. So I should be able to write or draw somewhat like this. From here, when I draw, I should have a reluctance like this, which is again for the side limb. And a similar thing should also be here for the other side limb. So this is also reluctance of side limb. So if I calculate the reluctance of side limb, each of them, because both this and this are coming in parallel, I'll get half of that reluctance as the resultant reluctance of this limb 1 and limb 2. So if I may call this as limb 1 and limb 2, limb 1 and limb 2 are identical, so they will not have much difference. So I can calculate, first of all, the reluctance of side limb. So I should be able to write this as, first of all, 500 multiplied by 10 power minus 3. Is it 500? No. I'm looking at the other problem. This is 340 and this is also 340. And the area, cross-sectional area is 500 mm square. So 340 and 340. So let me first of all modify this as 340. So I'm writing, what I'm writing is L by mu naught mu R A. So 340 multiplied by 10 power minus 3, mu naught is 4 pi into 10 power minus 7. And what is the relative permeability? Relative permeability is 400. So I'm going to have 400. And I'm going to have area. Area is 500 mm square. So this is the reluctance of the side limb. But resultant reluctance of two side limbs, that is going to be whatever we had calculated earlier. We are going to have this L divided by 2 mu naught mu R multiplied by A. This is going to be the resultant reluctance of two side limbs when you are going to have them in parallel. Now to this we have to add what is Rg and what is R iron. And then we have to use the total reluctance and divide MMF by the total reluctance so that we get the flux. Okay, so I can calculate what is Rg and what is R iron. Rg will correspond to this 1 millimeter gap and the area is 800 mm square. So I'm going to have 1 millimeter gap, which is 1 multiplied by 10 power minus 3 and 4 pi into 10 power minus 7. And I'm going to have area of cross section, which is 800 into 10 power minus 6. That is going to be Rg. And R iron, I can write this as, let's see. Let me just see this once again. This is only 150 mm. And area of cross section is 800 mm square. 800 mm square. So I should be able to write this as 150 into 10 power minus 3 divided by 800 multiplied by 10 power minus 6. And I'm going to have 4 pi multiplied by 10 power minus 7 multiplied by 400. This is going to be the total reluctance, okay, of this whatever is the main limb or the middle limb. So this is the reluctance of the middle limb. So this is what we just tried to calculate, and the parallel combination of limb 1 and limb 2, that reluctance is this. So if I say that this is R12, so I should say total reluctance is equal to Rg plus R iron plus R12. All of them will be added. Then we have to divide this. What is given? Actually, the flux is given. Calculate the MMF required to produce a flux of 1 milliweber in the central limb. Okay. So what is given is 1 milliweber is the flux. So 1 milliweber is the flux produced in the central limb. Okay, so that is the flux produced in the central limb. So we can say flux multiplied by R equal to MMF needed. So you should be able to calculate exactly what is the kind of MMF you need for establishing a flux of 1 milliweber in the middle limb. Overall reluctance of this magnetic circuit happens to be this entire thing. Any questions on this? Any questions? Please check it up because I am getting actually extremely large value of current. I want you guys to check it up. I am getting large value of MMF. Please do check it up. I am getting something like 6,354 or something like that. Please check it up. Okay. Last problem, I'll quickly tell you the methodology and I want you to do it. A magnetic circuit made up of a steel alloy whose relative permeability is 1500 has dimensions as shown in figure B. There is an air gap of 1.2 millimeter long on one side limb and a coil of 400 turns is wound on the central limb. The cross-sectional area of the central limb is 1600 mm square and each of the side limb is 1000 mm square. Calculate the exciting current needed to produce a flux of 1000 microweber in the air gap. That is what is being given. Okay. So for doing this, first of all, we'll have to draw the complete magnetic circuit. The magnetic circuit is going to be, this is the central limb, which is going to have the MMF. And that has the reluctance of iron itself or whatever is the magnetic material. Now, along with this, I'm going to have one side limb which is having a uniform reluctance because this is going to be again side limb reluctance. And the other side limb is going to have one reluctance due to iron and one more due to air gap. So this is what is given and you are given area of cross section for either of them to be maybe 800 or something like that, right? 1600 mm square and 1000 mm square. So this is going to be 1000 mm square and this is 1600 mm square. And you will have the length also given clearly. The length is given. For the middle limb it is 300 mm and here it is 500, here 250, 250 plus 1.2. So that is what is given. So this is 1.2 mm and this is 250 plus 250 and this is 500 mm and this is like 350 mm. So everything is given. Mu r is also given. So it's a pretty straightforward calculation, but only thing is the flux what you get here is phi total. And you have to find out how it is dividing itself into these two. So it is exactly like current division rule. What you use in the case of our regular electrical circuit, a similar thing needs to be done, and you have to divide this into two and find out what is the kind of flux you are getting here. Because the flux value, what is established in the air gap is, I think, being asked. No. The flux in the air gap is given 1000 microweber and the exciting current is asked. So please make sure that you complete the